why do we say it measures weight? Let's take a look at Newton's second law of motion. The total force acting on an object is equal to the mass of the object times the acceleration of the object. This is what I consider the most important equation in all of physics. This F here in the equation stands for the total force. If I am in equilibrium, what is my acceleration?
0.
So if in equilibrium, acceleration equals 0, which means that the total force, again, this is total force, is equal to 0. Well, I have two forces acting on me. I'm just going to make up positive. And so if I'm in equilibrium, my equation here is that I have y sub p minus w sub p is equal to 0. I'm just adding the two forces, one's positive, one's negative. So my normal force, the normal force I exert on the scale is equal to my weight. So this is why we say that it measures weight. But if I'm bouncing on a scale, it's not measuring weight, it measures normal force. If I'm standing still, it's measuring normal force, but the normal force happens to be close enough to the weight. When we get into chapter 6, we'll talk about why it's slightly off. And if we get far enough, I can doubt it in the 8-week course, but if we get far enough, talk about that there's one other factor that we ignore. I did a video which talks about the actual difference between your weight and what a scale measures, taking into account the fact that the Earth spins and the fact that we are surrounded by a fluid. Did you have a question?
No.
What's that? When it says acceleration equals v times, what's that small area beside it?
This?
Yeah.
Meters per second squared. I just put in units in.
Okay.
My weight is about 1,000 newtons, and the spin of the Earth means that that is off by, I think, somewhere around 2 newtons. So 0.2%. Scales are off. Yes?
How fast, because you said the rotation of the Earth throws it off a bit. How fast would the Earth need to rotate for it to be like a not even reliable unit of measurement anymore?
I'd have to work through that. I'm not sure.
Awesome.
Sounds like a nice test question. Test one B.
Thanks, Alan.
I'm trying to give him a headache so he knows how it feels.
All night give it us.
You shouldn't even bother with that. Just.
Well, when we get to chapter 6, that'll be a trivial question.
Surely.
So, if something or someone were jumping up and down on the scale,
Yes.
this is how we would eventually.
You can figure out the acceleration of the person and the fact that yp minus wp is equal to the mass of the person times the acceleration of the person.
Okay.
So if you know your mass, you can calculate the weight. So that's y sub p minus mg, the equation I had earlier, is equal to ma. G, I got a pretty good idea of that value by mass. I have a decent idea what that value is for me personally. So if I know what the scale is reading, I can calculate what the acceleration is. And this relates to one of the master set questions from chapter 1. I think we're ready for the next one. Box.
Oh, wow.
Yeah. You will deal with box on ramp far more than what we're doing right now. Because eventually, I'll be able to give you the angle, give you some coefficients of friction, and you'll figure out what the acceleration is. But that's for a different day. So box on ramp, so first thing I'm gonna do is this, I'm indicating that the ramp and the ground are part of the same thing. This is not box on ground, it's box on ramp. Ramp happens to be part of the ground. And a box. Now, when I draw them separately, I do recommend that you draw them in the same orientation of the original problem. Some people will straighten the box out. I don't recommend that because people who do that tend to mess up in another place. So I find it simpler to do it this way. You got a checklist. By the way, if I ever write F-town instead of F-tong, that's because I'm using weight instead of gravitational force. I do that for 110, but I do F-town for 110, I do F-tong for 251 for 151. Why? Well, presumably the typical chocolate scars. All right, what can we get rid of this time?
Gotcha.
All right. Let's start out with the simple one. Gravitational force. Which way is that acting on the box?
Downward.
I have only one small object, so I don't need a subscript there, so it doesn't. Now the one acting up on the ground, this is all one object, so some people will draw this W on the ramp because it's on the ramp, the box is on the ramp. That's fine, or in general, it's an arrow from center of mass to center of mass. It's upwards, somewhere on this monstrosity. That's it. Normal force.
Is it the box, the arrow on top of the box?
On top of the box. Going which way?
Right,
Right.
yeah,
That way?
yeah. And then on the slant, oh, going this way, diagonal, the opposite direction?
Absolutely.
Okay.
The biggest rookie mistake I hear, rookie mistake number whatever, 4, 5, whatever we're up to now, is people get in the habit of drawing normal force opposite the direction of the weight. It is not, it's perpendicular to the surface. So normal force is going up at an angle because the surfaces of contact is at an angle and the normal force is perpendicular to that.
What did you say the rookie mistake was?
To draw the normal force up automatically.
Okay.
So could you draw the gravitational going like that?
Gravitational force is, on the small object, is always down.
Right, down in the sense like when it's on that ramp.
Remember, the gravitational force, the weight is because of the entire planet, not just because of the ramp. If the ramp suddenly disappeared, the weight's not gonna be shooting off at that angle, the weight's gonna fall this way.
Okay.
It points to the center of mass of the other object, which is the planet. Right, and friction.
So the box will be going to the right, but it's gonna be on angle.
So friction acting this way on the box?
Yeah. And
So
then-
friction's making it go faster down the ramp?
No, shouldn't be. So is it supposed to be going the other way?
It opposes the desired relative motion. So from the ramp's point of view, which way does the box want to go?
Yeah,
Friction opposes that.
so it's supposed to be, okay.
And then the other part of that pair,
It's gonna be on the, it's gonna be a parallel to it, but the opposite direction on the ramp.
so two vectors that are pointing in opposite directions are considered anti-parallel, just from a language and vocabulary point of view. There we go, the force diagram of box on ramp. And this is one of the reasons why I don't use X hat and Y hat, is at this point, if the box accelerates, which way will it accelerate? Looking for a point, let's not define negative or positive yet. Which way will, if I put a box on a ramp, it's gonna, if it accelerates, which way will it accelerate? Down the ramp, yeah, it's gonna go that way. So we've set up our coordinate system for a problem like this. We would set up, I'd have I hat down the ramp, J hat perpendicular to the ramp. And most people, when they do X, Y, it is much more convenient to do I hat, J hat like that. Because when I do my equations of motion, one of them, if I have acceleration in the same direction or anti-parallel to one of my unit vectors, then my other equation of motion is going to be equal to 0. That makes the math so much simpler. As you get more and more sophisticated physics, there's more and more time spent trying to figure out how do we set up a coordinate system so that we minimize the amount of math we have to do. If you just love math and this is the end all and be all to your life because you have nothing else that you need to do, then by all means you can set up I hat, J hat like this and have fun. But if you want to solve it more quickly, you set up I hat in the, I recommend direction of acceleration, J hat perpendicular to it. Okay, 5 minutes. Questions?
Wait, was that ramp just taking into consideration, it's just on top of the ramp, or did we take into consideration that it already fell down from the ramp?
I put the box on the ramp and then I let go.
Oh,
And the
okay.
box is gonna do something.
Alright,
The box might not accelerate at all. It could be in equilibrium there, or it could be in static equilibrium, in which case it stays. It could be in dynamic equilibrium, in which case it's moving down the ramp at a constant velocity. Or it could be that it is going to accelerate.
but for this specific question, we're only looking at the initial, because if there was a final, we would have like the normal force on the ground and on the box itself, right?
You know, you're saying that the force diagram would change depending upon what happens, what the box does?
Yeah,
I'm saying it doesn't.
okay,
That these are the forces acting on it regardless.
alright,
Now, the value of the friction, is it static friction or kinetic friction? That depends on what's gonna happen. Yeah, we will get into the nitty-gritty of that one later. All right. Box on ledge. Box dangling. So let's introduce a couple more bits here. This right here, an ideal rope. An ideal rope has a couple characteristics to it. Number one, it does not stretch. It is stretchless, which for some reason is considered a misspelled word when I type it out. Stretchless means that if B moves, A moves with it. It's not that B is gonna go move down while A stays put. It's not a bungee cord. It is a massless rope. So I'm not worried about the weight of the rope. Now, if you put the weight of the rope into a force diagram, I don't take off for it because technically it is there, but it is so small compared to everything else, we're ignoring it. It also is frictionless, which means I'm not worried about the pulley turning. The pulley is ideal as well. Although, given an ideal rope, it doesn't really matter about the pulley. But the ideal pulley is massless and frictionless. So we will eventually add friction to the pulley, at least between where the rope will do away with the frictionless characteristics, so that the pulley turns. We'll do away with the massless aspect here. These we will keep in 151. In 251, sometimes we do away with the massless criteria. And stretchless, we simplify. As far as ropes go, they would stay stretched. But I would like to think that all of you could actually do the force diagram. One other thing here is that when you separate it, because now you have this pulley and the ground, do I treat the pulley separately? So when you get to the complex test level force diagram problem, which will probably be the next to the last problem on, no, probably be next to the last problem on the test 1B. I break it up for you so that to eliminate the what goes with what. I typically put the pulley as part of the ground. So this is, in essence, a 4-body problem. When it comes to the analysis, it will be reduced to a 2-body problem, but we'll get there.
So the only thing that won't be considered in there is other, and then the rest will be present, so there's friction, tension, normal gravitational in there.
Yep. There is no other. It can be if you want. That was a horrible Sean Connery. It can be if you want. Anyway, on that note, and for all you international fans who want to do better Sean Connery, make sure you put it in the comments, not a video, just write in the comments, your better Sean Connery imitation. In college, somebody put an ad in the school paper of, basically gave the number to an answering machine, and that it was God's answering machine, just call if you want to talk to God, and just to see what would come up. So I'm curious if someone could actually type in text a Sean Connery invitation.
Pre-internet world must have been so crazy. You can just get away with this.